Hello.
20 vocabulary words coming up.
Here we go.
Lots of animations too, so we gotta beat feet and take care of business.
There you go. So first one, kinetics.
Look at that cold one's moving awful slow and they ain't hitting each other. Zizzes.
Yeah, and that hot one's moving really fast and they're banging into each other.
And if you're looking very carefully, the colors are changing a little bit, showing that a reaction has occurred, which means our vocabulary word,
Kinetics, studying the rate of the reaction.
How quickly does something happen or how quickly does something not happen? That's what the whole umbrella of kinetics is.
Yeah, you can actually, maybe put quotes around rate. Rate is going to be a key word for this whole unit.
Yep, definitely.
Okay.
Reaction rate.
Again, so now it's per time, so that's why there's a little clock in there. And that's just going to talk about how quickly the reaction actually occurs, time versus reaction. How quick is it? Is it a fast reaction or is it a slow reaction? Some are different.
Collision theory, mad important. You can see these particles colliding. And sometimes, if they hit just right, the colors will change, showing that a reaction has occurred. Collision theory itself, definition-wise, is the idea that describes what it takes for a reaction to occur. It starts with a collision of reactants.
And a special set of circumstances to make the reaction go.
Right.
And then once we know what that is, then we can effectively manipulate it.
Mm-hmm.
Right. And then what that is what we call an effective collision, which is next.
Bingo.
Because it doesn't work without it. So let's watch this. Let's go through. There's two molecules collide. If the collision is effective, it has enough energy to break the bonds, and now it's reacted and made new molecules, and a reaction happened.
And that's what it is. So collision with enough energy and correct orientation to start a chemical reaction. It's a lot like a handshake.
Sure.
Correct orientation, nice shake.
Right.
Business relationship
now
established.
Do it again. Same here. You go like this.
It
doesn't
quite
work.
right.
Wrong orientation.
Right. Not really a good handshake.
Right.
Good handshake, effective collision. Bad handshake, ineffective collision.
Right.
That's what's up.
That's it. Literally is
Catalysts.
what's it.
Catalysts.
So this is referring to the dotted line, the red dotted line. You see how it says reaction with catalyst?
Reaction without catalyst.
Yeah, muy importante. We will never call that without catalyst, but this is showing you what a catalyst really is. Gives us a different path.
Right.
So a catalyst is a substance that speeds up a chemical reaction, but here's the key. It's not consumed. It's actually preserved. If you put in 6 grams of catalyst and the reaction happens, you should have 6 grams of catalyst done at the end. Otherwise, I've actually changed the reaction.
Right.
So it doesn't do that. It just gives a different pathway. It actually makes it faster.
Catalysts are tools. I can cut paper without a scissors, but I can go a lot faster and quicker and with a lot less
And more
energy
precision.
used on my part if I use the right tool. And when I cut paper with the scissors ain't broke. I can keep using it. So a catalyst is like a tool.
It is.
Makes reaction
But it's a
happen quick,
chemical tool.
isn't used.
Thermodynamics. This is really just the study of, you see that thing on the left? Well, heat.
The Sadie Carnot's heat engine.
Yeah. And in our case, we're going to look at entropy, which is heat of reaction, and enthalpy, randomness and disorder.
You got them backwards, but you're
Oh,
right.
I did.
They're both E words. So
I think I got
notice
him here.
it's very, very challenging. Entropy, enthalpy, they're very similar sounding,
are.
mean completely different things. Why are we going to do that again? Because,
Yeah, we're chemists.
they made chemistry hard.
Yeah. Not our fault, actually.
Yeah, right.
We didn't come up with these words.
Nope.
But I did show you how easy it is to get them mixed up, right? So are you going to make that same mistake? There's the real question.
A potential energy
And
diagram.
we've seen these already before when we were talking about endothermic, exothermic. That's going to come back again. But what we're going to do now is see where all those numbers are. We need to be able to
Label them up.
Right. So this is just a diagram tracking the potential energy from reactants to products, and that's what it is. So it is a graph showing the difference
Between
reactants and products in terms of their potential energies that they have.
how much heat those molecules have stored up in them before and after the reaction, or
Right.
before and after the reaction.
Right.
A heat of reaction, I love this animation because it shows us not only activation energy, which is a later word, but the heat of reaction itself. If you see very carefully, as that particle rolls over the hill, it comes back down,
Boom.
and it releases the energy that it had stored up in it.
Yes, it does.
That's what heat of reaction is.
It really is. And it's specifically
The change in the enthalpy of a reaction. We call it delta H. We calculate it by subtracting the energy of the products in the reactants.
Yeah, and but it needs to be in this order because
The
subtraction
sign
is not
matters.
cumulative, and the sign matters tells us if it's endothermic or exothermic.
Yeah. And here's some more enthalpy diagrams.
Yep.
You can see delta H is negative on the left-hand picture, and delta H is positive on the right-hand picture, again, due to the order that you have to do your subtraction in.
Right, so the sign is important, and we have talked about this in the past, so we should have an okay sign. We've had or an okay time with this. We have had to draw these before. We're just now without the labels. Now we got them.
Let's put the pedal to the metal, boss.
Yeah, come on.
Delta
Right,
H,
so
there it
here's-
is. Write it down.
Okay, we go faster now. Entropy, we are going to deal with this in states mostly. So highly ordered solid, aqueous or gas has got a lot more disorder and a lot more movement, a lot more randomness to it. So entropy is just the study of disorder in the system. The law of thermodynamics favor greater disorder because order takes energy. Nature wants lower energy, so actually disorder is lower energy.
Forward reactions are simple. They're the same type of reactions you've seen all year. The arrow for the reaction points to the left. I'm sorry, the right.
Right.
It points from the left to the right, meaning
right. And on your
forward
screen
reaction.
is that this? Oh, I can't put myself in your shoes.
They're
That might
watching
be
it
right
from
to
the
that.
same direction. It's this way.
Okay. But you can see
Reverse reaction is, well,
the
the reverse.
Forward is going from left to right.
Reverse,
Going the other way. Notice this picture is showing you both.
right, and left.
Ooh,
So-
that's going to help us understand what equilibrium is. Activation energy. Whoops. So again, up into the top, the energy needed to get to the top or the activated complex at the top of the hill. The energy I got to give those reactants to get them to go.
Yes.
The energy needed is the activation energy.
Sure is. And there is the activated complex. This is the moment at which all the particles are rearranging to form the new bonds and produce the products.
Right.
Maximum energy state begins the formation of the products, like I said.
Yeah, the complex is a noun. The energy is more of a verb. So it might help us differentiate between those two. Equilibrium. Forward, reverse. Forward, reverse. That's really what this
at
means.
the same time.
So this is the state where reactions are happening in both forward and reverse reactions at the same time. So we're going to find out that the concentration is constant, not the concentration is constant, not necessarily the amounts.
Right.
The grams don't have to add up, but the concentrations stay steady.
But you go on.
And we got
Physical equilibrium. When a liquid evaporates and condenses and comes back down, forward and reverse rates of melting, freezing, evaporating, condensing are equal.
Yeah, as one molecule goes into the gas phase, some molecule in the gas phase has to come back to the liquid phase. Happens at the exact same time.
This is a graph of a chemical equilibrium.
Right.
It's not exactly what we're talking to you about in this unit, but you are responsible to know that a chemical equilibrium is,
Well, those flat lines show that the equilibrium now, the rate of the forward reaction equals the rate of the reverse reaction, and our concentrations are constant. And that's really what that picture was showing us. Because as one is over here, they go this way, and the concentrations stay the same.
solution equilibrium. Well, when a crystal at the bottom of a beaker dissolves, a dissolved crystal must precipitate.
Very much like the physical equilibrium, except for this one's stuck in a solvent. Right?
Rate of dissolving equals the rate of crystallization.
You notice in these last three, rate was highlighted and underlined. Rate is important.
Yep.
Now, this last one, this is Le Chatelier's principle. It's tough to say. It's pronounced Le Chatelier's.
Yep.
I do not have this Knox tube for you, so that we're going to give this one a second to let it play out. You see its color in the cold,
Very light color.
and then you put it in some heat, and let's watch what happens to the color.
It gets darker.
It gets darker.
So this is a stress. The principle is a reaction at equilibrium will shift to react to that stress.
And to get back into equilibrium.
And equilibrium, stress, and shift. Again, we don't show you these graphs aside from here, but what we're trying to show you is that when you change the concentration of something,
It shifts.
it shifts the equilibrium. So let's see our definition.
So the change in concentration, heat, or pressure will cause an increase in the products or reactants. We will get a way to decide, does it go left or right? And that's it.
It is.
That's our
Thanks
last
for
one.
watching.
Be ready for your quiz.
See ya.